Cool, thank you. Great, so we're gonna talk about pragmatics, program analysis and or static analysis. And essentially the goal with this is basically talk about how I use it or have used it for security research, or how it can be used for enhancing your security research endeavors. Cool, so we're gonna get nerdy, pragmatically speaking. Great, so who I am, go by Hexapunk on the interwebs. Alex Useche is my name. And then I am currently the senior staff security engineer at FullStory. I do product security at that company. Previously, I was at TriloBits doing all sorts of things. I was the director of application security services and also principal doing IC stuff. Before that, a bunch of other different things. So doing different sorts of AppSec, consulting type of work, pen tester, help desk, tech support, and also worked as a software engineer for a few years as well. I will point out that I suck at math, but I like to think that I'm good at programming, weirdly. Though I do have some theories as to why that might be. I point that out because I point that out, and that will become clear later as to why. Great, so these are the things I like: program analysis, programming languages, PLT, which is programming language theory. That's basically the theory behind how programming languages are compilers and interpreters and all that sort of thing. I touch way too many programming languages, so I easily get distracted with new, shiny, interesting programming languages that come out. Also like digging into Kubernetes, cloud-native software, and that's a lot of what I used to do at TriloBits as well. I love writing code and all sorts of other things, of course. And I hate the idea of the born genius. I like to think, at least, that we can learn anything if we put the right amount of effort and the right amount of rigor and discipline. I also dislike knowledge monopolies, basically the idea that only certain people hold the type of knowledge that you need to accomplish certain things, and you need to go through, I don't know, some sort of fancy degree to get the knowledge that others have. Also dislike the idea that try harder means not asking questions as well. Great. So I love this quote, which is, we are not what we know, but what we're willing to learn. And I really like the quote because I found initially program analysis and static analysis sort of confusing and just sort of intimidating is the word that I was looking for. And I was very intimidated when I started looking at the literature for this, but it turned out not to be that difficult. And then part of it has to do with continuing to go past any hurdles that you might find. Great. So there's something else in this. I just keep going on the same soapbox, I know, but I'm here, so I'm going to go ahead and do it anyways. So there's this thing about neuroplasticity and the mind, and then it requires two different chemicals that are associated with error and frustration. And the idea is that basically neuroplasticity occurs once you you experience those two error, you commit some mistakes, and then you start experiencing frustration. And once you get past that, then neuroplasticity starts occurring, and magically you start sort of learning things. So I think that that's something nice to keep in mind when you encounter things that are sort of difficult to learn. Great. All right. So this is in Go, and a lot of my samples are going to be in Go because I have worked a lot with Go, primarily. Now, there's a bug here. If anybody is familiar with Go, let me know if you see the mistake or the bug. I'll just wait like 5 seconds because there's a lot of content to go through. Great. So there's a function, get result A. With parameter 1, get result B. Both can return an error, and then we are checking the error at the end. If error doesn't equal nil, then we do this. We print to the console. Now, if you notice, we're only checking the error from the last get result B, but the error from the first one, for the first call, gets overwritten by the second one. This might seem innocuous or just not a big issue, but a lot of security issues start this way. At least that's what I have found in the work that I have done before reviewing tons and tons of code bases. Particularly in Go, this is a common issue. And this is C. So, and this is a fairly tricky one for many people, but take 5 seconds to see if you find the issue. Like I said, it's sort of a tricky one. I don't have a good sense of time, so I'm going to go ahead and say that that was 5 or 10 seconds. I don't know. But essentially what's happening here is that we are copying the first string into the second one. So the stir copy here, we have the parameters flipped. So essentially when we print this, we're going to get garbage. We're not going to get what you think we're going to be getting. So that's what's happening here. And this, again, it's a might seem like innocent sort of issue, but depending on the right context, it can be a fairly serious security concern. Cool, and this is one more. This is back and Go. And this one I'll just explain right away. So basically there are locks that we can hold on mutual exclusion locks, basically, and we can hold that data so that no other routine touches this particular object when we work on it. So we call the lock function here. And then at the end, right before we return from this function, we release the lock. Now, what happens if the name equals the letter C is that we return without releasing that lock. So that's another issue that I have seen sort of commonly in Go code. And another one of those that looks innocent, innocuous, etc. But if this is, for instance, on an API call or an API endpoint, you encounter this situation where there's a missing unlock, then you're going to end up with a API endpoint that becomes unresponsive. Cool. So the question then is, can you just use regex to find these bugs? Probably, at least for the first one, you can probably just mess with create some fancy regex, which I suck at, by the way, and that will allow you to maybe find that particular bug. However, the tool will probably need to be a bit smarter, and we'll probably get a lot of false positives. For this particular function, which was our second example, it will be a lot harder to find this by regex alone, because it will need to be smart enough to be able to tell that we actually flip the parameters in the call to stir copy. So that's where program analysis comes in. Program analysis, the cool thing about program analysis is the idea that there are programs that reason about programs, and I find that super cool. So it's a program that infers about a program by inspecting its code. This is without execution for the most part. There's this whole area of study in program analysis called symbolic execution that it's sort of a mix of the two. And I won't go into that, but it's super interesting as well. Cool. So where is program analysis used? Not just in static analysis in tools and linters. It's heavily used in compilers. It's used for memory leak detection. It's used to simplify programs at the compiler level, finding error patterns, linting in IDEs, and obviously SAS as well. Static analysis, secure. Well, I always forget what that means. But static analysis tools for security. Cool. So compilers, yes. Program analysis are the core optimization routines. So for instance, this is static analysis is so used to determine that if the developer wrote the code that's on this side, my right, but behind me, then the turns into the code on the other side of the screen. So basically, we are removing any unnecessary code that the compiler deems as sort of garbage, like it's superfluous. Now, why should security nerds care? Like I said earlier, it facilitates security research, particularly for open source tools. So like If you go into HackerOne or any other bug bounty platforms, they often will have programs where they point you to their GitHub repo, so you can actually go and find it and obviously clone it and then start performing static analysis on them, whether that is manual or running as tools or writing tools to facilitate your analysis. I also saw a video recently of somebody that was using SamGraph, which is a tool that I'll mention later. And what they do is they go into doing their typical dynamic analysis of a web application. They get to the site and they basically download the source code if it is not completely minimized. And then they run static analysis tools on it to find bugs. I thought that was pretty cool. Cool. Program analysis goes beyond simple SAS tools, like I said. It can also statically find race conditions, can create very smart fuzzers, automatic test generation, symbolic execution, like I said earlier. And these are some tools for automatic that I put it there in the wrong bullet point. Those are tools for automatic test generation, which are pretty cool as well. Cool. Now, when you start learning program analysis, if you find the actual sort of academic literature on it, you find a lot of math. That you cannot see that, but that's a lot of math, basically. And a lot of mathematical notation that it's kind of like those memes where it shows you how to draw, and then it shows you some simple lines, and all of a sudden you have Da Vinci or something amazing. You're like, how do you go from step 1 to step 20? That's kind of how I felt when I started going over the program analysis literature. Started fine. I was like, I'm getting this, and then it was like, math. I don't know. I failed math in 9th grade. I failed a couple other math-based things later in high school. So I had a difficult time figuring it out. I later sort of like pushed through and was able to figure some of the basics that they were trying to communicate there. But later, I started just learning about compilers and interpreters. And I found that those were much better resources to learn about static analysis tools, because they tell you how programming languages are, how compilers and interpreters are able to grab something that a developer writes and make that run or compile it and find issues in the syntax, things that you were not, hey, developer, that's not what I meant for you, how I meant that function to be used, etc. This is a great book called Crafting Interpreters by Robert Nystrom. I don't know how to pronounce it. And he wrote Dart, which is a sort of kind of like TypeScript, but not TypeScript, but sort of basically a language on top of JavaScript. So it's Dart, CoffeeScript, TypeScript. Dart is one of those. And the book is great. It touches interpreters, not compilers, but the second half of the book starts touching on compilers, and it's a super great introduction to the field. Then you can also go over the specification of the languages that you are trying to learn, especially the ones that you want to start focusing on in terms of static analysis. So this is the grammar specification for Go. They basically start telling you how they understand function types, what are functions made of. So those are very nice, very easy to read resources, and that's for Go, but there are other, you can find the same for any language of your choice. So here we go, we're gonna dive into some more, some theory here. Cool, so a good way to start understanding static analysis tools, and part of why you wanna do this as a security person, again, it's not just so you write your own static analysis tools, but also so you understand the tools that are available, the many tools that the vendors are going to try to just reach out to you via LinkedIn and try to convince you to get in exchange for a DoorDash car or something. It helps to at least know what the underlying technology lies underneath those. And this is great. It allows you to select the right tool for the job as well, whether that is a paid tool or if it is a open source tool. So there are two main categories, procedural and interprocedural. One of them is restricted to finding the, do an analysis in the code that's inside individual functions. So think intranet, and the other one is interprocedural. So it's basically it's able to understand the relation between different functions. So it's able to say like, hey, this particular function gets called by this other 5 functions, which get called by these other 5 or 11 functions. Every static analysis tool typically has 3 goals: soundness, completeness, and termination. But not all of them are going to be able to, or actually not any one of them is going to be able to accomplish these 3 properties. So one is like no false positives. The other one is if there's a bug, completeness, which is if there's a bug, it will find it. Termination, that it will finish. Basically, it won't get stuck in infinite loops and whatnot. Cool, and these are the methods. Now, when we go over the methods, it helps to understand that program analysis, it's all based on abstractions. So that means that we have code, and how can we abstract that in terms that we can sort of start manipulating in order for us to start understanding what the program is actually doing. And one of those abstractions is abstract syntax tree. That's basically a simplified syntactic representation of code. It discards any grammar not needed for analysis. And there are many tools that are based on an analysis of the abstract syntax tree alone. So they aren't super smart, but they do a good job finding basic issues such as, hey, you're using this function insecurely, or you're using this insecure function at all. So anything like, for instance, in Java, there is the math.random instead of secure.random. So if you're using math.random, it's simply gonna look for those functions. It's gonna say, hey, bad function to use for cryptographic purposes. So this is what an abstract syntax tree looks like. So if you have something like 4 times 2 plus 3, that gets broken into, and then return a plus 2, it gets broken into its core components like this. So you have the different data types, the value 4, the value 2, the value 3, and then you have the operators, so the multiplication and the addition. So that's basically, you break a statement or a few lines of code into its basic components like this. Cool. And then there is this concept of CFG. CFG is control flow graph. And then what they do is basically they map the relation between different statements in code and or different functions in code. So it's able to just draw a graph to determine how the function flows between if statements to return statements to loops, etc. Cool. And this is another sort of representation of CFGs. And there are tools like Facebook Infer and GoCart, which are, I think Facebook Infer is open source, I'm pretty sure, which do analysis of the control flow graph of the code. Cool. So knowing those 2 concepts, we can understand now the general approach to most static analysis tools. So they first generate, and they grab the code that you are given it, they create an abstract interpretation of the code, then they remove anything that is not important for analysis, and then they build a control flow graph for interprocedural data flow analysis, and they build another one for interprocedural data flow analysis. So one, so you can understand again, here we go into an if block, here we're going to a loop, etc., and the other one to understand the relation between functions. And then it builds something called a computational tree, which is basically just a big graph that shows the flow of the program. And then once it has this big abstraction of the program, then it conducts some sort of analysis based on that abstracted program. And then we can go back to compilers to understand that basically they follow the same process. They read the source code, they generate the abstract interpretation tree, they create a control flow graph, and then from there might be other steps included there to create some sort of intermediate representation of the code, and then they create the object code. So if we see the Go compiler process, it's similar to that, which is it parses the code, checks for types, it creates some immediate representation, and then it walks the different statements that were created and generates something called SSA, which we'll describe in a few. Cool. So this is why you want to choose a tool that uses one type of abstraction versus the other. Depending on the analysis you want to conduct, one might be flow sensitive and the other one flow insensitive. So anything starting from the simplest type of tool that uses just either pattern matching or abstract syntax tree analysis, it's going to be very fast, but it's going to have a lot of false positives. And as you start using more advanced techniques, such as data flow analysis and procedural analysis, then you start getting less and less false positives. So next time you have a vendor that is promising some amazing static analysis tool, just ask them what type of analysis they're doing. Great. And then there are other techniques that then, once you get further in the chain in this graph for the more complex techniques, you get into things like lifeless analysis, which is how long can a variable survive in the program, pointer analysis, dynamic symbolic execution, and all these are sort of, it allows you to run static analysis tools at the same time that you keep getting less and less false positives. So getting started with static analysis, a great tool to get started with understanding hands-on how static analysis tools work, because it allows you to create your own rules and optimize a system or tweak a system rules very easily is SemGrep. It's a tool that I really like and I highly recommend. It's a static analysis engine used for discovering bugs and finding patterns, defining rules written in YAML. I know YAML is not the favorite of many people, but it's super simple and super easy to use. Now, it's usually you want to use it when the bug that you're trying to catch should be easy to identify in different patterns. If you can find the bug looking at single files, so it's not very good at. It can do analysis based on multiple files, meaning that you have one function here that calls a dangerous function there. You want it to call out those relationships. It does some of that work with the Pro version, but it's not the ideal tool for that sort of situation. If you need cross-functional analysis, then you probably want to use something else. And if the bug is systemic, there might have multiple instances across the code base, like a misuse of a particular function, it's a great tool for you to use as well. It does intra-procedural analysis, like I said, doesn't focus on path sensitivity. It doesn't do anything like pointer or shape analysis, but it's great. For most things, actually, SemGrep has been an amazing tool. This is basically the process, and in the case that you use it for Go, for instance. So it grabs your Go code, then it parses it into a CST, which is an app like a concrete syntax tree interpretation of your code. Then it creates a Go CST. It converts it to a generic AST. Then it creates its own SemGrep type of AST. So it does this different transformation. It transforms it into an intermediate representation of the code. And this is what a lot of programs do. They always need some sort of intermediate representation of the code so that they can perform analysis on them. And then it uses a matching engine, so it matches rules that you define in YAML against the code that you are seeing. So let's see some building blocks of SemGrep. So here you have a set of functions, or these are ways that you write your SemGrep rules, actually. So let's say that you want to find any function called request.get where the verify value is equals to false. This is all you have to write. Obviously with a little bit of like YAML, with YAML syntax, but you just do request.get, and then you use this ellipsis to tell it like, I don't care what's here, and I don't care what's here. I just want to find anything that's request.get with verify equal false. And that's going to match any of these functions. Anything that you have with verified false as the first parameter, as the second parameter with 3 parameters total or 2 parameters. So it's pretty nice and easy in that way. You can also find specific types. So you define the type in parentheses, and it's going to find those particular types whenever you want as well. In the case of the missing unlocks rule that I showed earlier, this is a simplified function of that, or example of that same bug, where you have a return before you unlock the mutual exclusion lock. This will be what the rule will look like, right? So you tell it that you're looking for a pattern where you have a panic or a return, and then the pattern is inside a call where there is both a lock and an unlock. So basically, these 3 dots say that the pattern that you're looking for, it's in between these 2 things. But what your pattern, it's not inside. So when SemGrep analyzes the code, it's going to notice that there is not a unlock for that particular type. So once it finds that, it's going to find that it has a match, and it's going to give you that. It's going to return that error or that finding. And this is what that looks like in practice. This is using the SemGrep playground, and this is a more sort of realistic example of that particular function. And this is the rule. And this is the actual matching that it discovered. So it's pretty nice, and this is actually one of the rules that I wrote that back when I was at Trilobits, and it's available in the public repository of SemGrep rules. And whenever you run SemGrep by default, it's going to run this as one of the many rules that runs over when you run it against Go code. It also has taint mode. What that means is basically you can define a source. So let's say here a source is get user input. A sanitizer, this is we're going to check if it's safe, and then a sink. So you have source, sanitizers, and sinks. And sinks is basically the bad function. I put sink here, but it could have been like a SQL call, for instance. And this is what that might look like. This is sort of like fairly advanced compared to the type of analysis that I showed you earlier, in that it does some of that data flow analysis, and does a little bit of that as well. It also has some newer features that are pretty nice, like it does interfile analysis for, I believe you have to pay. So excuse me, SemGrep, if you watch this video, or and that's not the case. But look it up. Then it also has some features called deep SemGrep, constant propagation, and symbolic propagation. All those are documented and make the tool much more powerful. And you have data flow. Let's talk about some data flow analysis tools. These are tools that work in reason about the flow of programs. And these are tools that do much more advanced type of analysis. Like I said, in these cases, they're going to be able to determine how the connection between the different functions. So your sources can be in a file 10 directories deep, and your sinks can be in any other file, and it should be able to find that. Cool. They are based on CFGs, control flow graph, and they are used by bug finding tools and IDEs and compilers for optimizations, etc. They rely on something called chaotic iteration algorithm, if you're curious. Cool. One of those tools is CodeQL. It's developed by GitHub. It's much more powerful, but it's much more complex. The queries are written in a language called QL, which is declarative and object-oriented, so fairly advanced, and it's based on data log. That's all to say, it's much more complex than SemGrep. It's not YAML. Cool. So you will use CodeQL when you need interprocedural analysis, when you can build the code, because it needs to build the different intermediate representations of the code that require that the code build. And then it's going to take a lot longer than SemGrep because, again, you have to build the code and it does more extensive analysis. And also, your code has to be either open source or you have to pay for a license. So something to keep in mind. This is what an example of CodeQL looks like. And it's just much more complex. This is to find a open redirect in code. And here you are defining sources and sinks. So, and this is one of the simpler rules that I could find, and this is in the repo. So I won't go over that one too much because it's, in my experience, it's a great tool, but it's just the complexity is so high that it's worth, usually you can find the same type of issues with a SEMGraph most of the time. Cool. Then there is this other idea of region definition analysis, which also CodeQL uses as well. It determines whether a given value for a variable can reach a certain part of the code. So that is too little there. But that basically says that if variable x, for instance, is assigned the value 2, can x with the value 2 assigned reach the particular part of the code? And if not, by the time that we exit this function, what will be the value of x, if anything different? And then these are the properties of those type of analysis, which CodeQL relies on. It's not complete, so we'll find false positives because it considers all paths to be executable. It will report all facts that CUDA program runs, and will terminate. So it basically won't get hung up on if there are anything like infinite loops. So why should you use SEMGraph and CodeQL? The cool thing about these two tools is that I think they changed sort of the way that we do AppSec and the way that we do that we work with SaaS tools. Because previously you get tools, you pay for some fancy static analysis tools which you incorporate your CI/CD, great, you run it, but maybe the rules are not working very well, maybe you see a lot of false positives. Typically there wasn't much that you could do about it unless you call the developer and you tell them that, hey, this rule, it's crap, or you give them feedback, and then they work on their secret sauce and then develop the particular rules, and they maybe make some improvements to the tool. In this case, you actually get to have control over what your SaaS is actually doing. You can grab a rule and change it if it's not doing what you want. You can change the risk rating. You can change the name of the function. If you have wrappers around a particular function, you can do all sorts of things. At where I currently work at, we use, that's a lot of our process for static analysis, is we're actually developing a lot of custom rules, or we're optimizing existing ones, and we have significantly reduced false positive. Okay, so then there's this other technique called single static assignment, and this is used by a lot of compilers, or by some compilers, including Go. What single static assignment means is that you get a program like the one that's over there, if I'm facing that way, my left, and then where you have the variable x and the variable y and the variable z, along the life of the program, it takes different values, right? So here, x takes the value 5, but then later it takes the value y times 5, etc. Same thing for y, same thing for z. So single static analysis, what it does is, anytime that x or any variable takes a new value, we're going to give it a new name. So in this case, x, we call it x1 when it takes this value. And then here it's going to take a new value, so we call it x2. And that is going to allow us to be able to answer questions such as those that I mentioned earlier for if x takes the value 5 here, at the end of the function, can we answer whether that same value still exists there? So this allows us to answer things like, if we're taking user input here and storing it in this variable, by the time that we use it in this other function, which could be a SQL query, have we done any sort of sanitization on that particular value? So that's a very interesting technique. It's already implemented by the compiler in Go, so it's not something, you don't have to dig into the weeds as to how it works, but it's because they use it, it's a tool, it turns into a tool that you can use to do your own source of analysis. And this is what I did with a tool called Wally, which is open source. and I wrote this here. And Wally is a static analysis tools for thread model automation and attack surface mapping. So basically, what it tries to solve is discover HTTP and RPC endpoints in Go code. So mainly Go code, or actually only Go code. The reason why is because I started encountering a lot of monorepos, both as a code auditor doing consulting, but also in my current job, where we have monorepos that consist of multiple microservices. And anytime that I wanted to find out, is microservice A connected to microservice Y, it was very difficult to trace it back, or I had to do a lot of manual investigation in the code and trace back a particular call to see if I could get to that. So this tries to solve that by doing static analysis using some of the techniques that I mentioned earlier. It basically detects all possible paths from service endpoint A, which an endpoint can be an API endpoint, to service endpoint Z. So basically, an attacker can say, if you do analysis of the code base, of course, if I send an input to this particular microservice, will it reach this other highly sensitive or highly privileged microservice that's very deep in the internal network of the company? So automates initial threat modeling by code inspection, automates architecture and design analysis as well, and gathers data for targeting services during pen tests. It also helps with attack planning. Like I said, if I want my data to reach service Z, which endpoint do I need to hit first? Cool. It uses the same libraries that are used by Go to already run its own types of analysis. There's a tool called GoVet, which even when you build code, it's going to run GoVet to find any obvious issues in your code. So a lot of the same issues that uses, a lot of the same libraries and tools that uses are using in this particular code base. So this is basically the core of building static analysis tools, is going into seeing what's available for the language that you are interested in. And in this case, I'm interested in Go, like I said, and finding what libraries are useful. And these are the main libraries that I use for Wally, which are, there's GoAST, GoToken, and these are the different reasons why I use them. So we have one variable that actually generates the call graph, given an SSA program. There's a variable package for parsing packages, etc. So there's a lot of wrappers that you can use, and you don't need to know any math. It's kind of too little, but essentially, this is what a basic analysis, a simple static analysis rule might look like in code for Go, for instance. Which all we're doing basically is we're inspecting the AST, which is the abstract syntax tree of the program that it generates, and then we're looking for functions. So when we say hey, is this particular node a function? If it is a function, then we get the information from the function, we examine the type of package, we look at the name of the function, and if it's a function that we do not like or we do not approve of, then we can report it as a finding. It's fairly simple. There is a lot of this code actually for doing some of the, so a lot of the code that I showed you, basically it's coming from libraries that are already wrapping a lot of functionality for you. So I wrote a library on top of that to wrap even more usages, so it's even easier for you to use. So this is the sort of design flow for Wally. I won't go into detail, but basically all it does is basically parses the AST, and then it starts trying to find different functions that you tell it that you want to find. It determines whether it's an HTTP endpoint, an RPC endpoint, and then based on the different matches that it finds, it tries to map them together based on a call graph that is generated for you. So again, it finds all the different matches for the RPC endpoints, HTTP endpoints. It can be a handler, it can be a client call, and then for each one of those, it's going to do this, which is it's going to extract all the caller edges, then it's going to navigate those edges to construct a tree, a dependency tree essentially, and it's going to solve all those paths for you and print it out. So I'll just show you a quick demo of what that looks like. And this is essentially an interesting way, at least I think an interesting way of using static analysis techniques is to solve interesting problems like this. So this is me calling Wally. I'm giving it a definition of a file called wally.yaml, and the wally.yaml has a number of indicators I want to find. Those look like this. So an indicator just says, hey, I'm interested in mapping the relation between these particular functions. There's the forward function, the RPC function, and the query function. And I'm interested in you solving the value in the code, wherever those might be defined. If it is defined at the time of compilation of the code, I want you to resolve the value for the variables endpoint, method, and method for the function forward. And then I tell it to restrict its analysis on only, and I'm running this again against the Nomad code base, which is sort of like an alternative to Kubernetes. No sense in describing it too much further than that. So basically, it starts doing the analysis. Takes a bit because it does a little bit of analysis based on the SSA technique that I mentioned earlier. And then what it does is it essentially finds those relationships. The output here isn't super pretty, something that I need to make prettier. But essentially, this is a good one where it says, hey, I found this function that you wanted me to find. That's a register handler. And these are the different places where I found it. Or this is one place where I found it. Now, I found it here in http.go in line 526. And these are all the ways to get to that function. You can get, so if you notice, every path ends with that particular register handler's function, and you can see all the different paths. You can get there from new test agent, from this particular run. So then that starts giving you an idea, either whether you're doing some sort of threat modeling or you're doing trying to determine the relation between microservices and a monorepo. It's going to allow you to see those relationships as well. And then the nice thing is that it also builds or runs this this graphic interpretation of the code as well. So it maps those functions like so, where you select a particular function and it shows you the different ways that you can get to that. So let's make it a little bit smaller. And anytime that you select a red node, it's a finding. It's anything that you actually wanted to find, so that will be an API endpoint or an RPC endpoint of some kind. And I'll just refresh it because I think making it bigger or zooming in just mess things up a bit. And then there's obviously some work that I need to do on making this a little bit more readable. But this is basically it. So you can select this, and it shows you the different paths for that particular function. So yeah, that's a pretty nice way to use static analysis, and you can see the code available online, and I'll show you the link later. Okay, it was developed, this is how I developed it. It was researching existing OSS, open source static analysis tools, whether they are SAST or linters. That means going over their code bases and seeing like, how do they determine what a value is in a switch statement? How do they determine what the connection between a function call and a caller and a callee is, etc. I researched assistant tools available for Go, which resulted in the list of libraries that I showed you earlier. Read the program specification, Googling, and asking questions. Just jumping into the official Go Slack and asking questions there, even though I felt sort of scared to do so a few times. Cool. So that's the main thing that I wanted to communicate, is sort of trying to show you how static analysis tools use and kind of show sort of demystifying some of that as a way to hopefully motivate you to dig deeper into this interesting area of security, my opinion. So I think program analysis is cool, can make you a better security tester and researcher. I missed the R there. Can also make you a better programmer. because it allows you to better understand how the programming language that you are working on or with, how it works under the hood. For next steps, I think if you are interested in this, just don't be intimidated by the math. Most likely, most of what requires that level of math is already determined by your language of choice because they needed to do that for the compiler or the interpreter. Learning about interpreters and compilers is much more helpful than learning some of the more academic and mathy complex literature on this. Read source code. Reading source code is very important in my mind. If you dig into the code base for CodeQL, for instance, which is available on GitHub, it shows all the different languages that it supports. And if you look at each language, you can start learning how static analysis is done for each language, which isn't unique to CodeQL. It's just, that's all CodeQL is using. It's using tools that are already available in wrappers, in libraries already available for the language of choice to do its sort of analysis. And then start by writing simple tools. So anything, I will recommend working with SemGrep. It's a great utility to start working with. I have found several bugs that I have reported to open source systems or open source libraries like by Microsoft and Kubernetes as well. So go ahead and start diving deep into this. These are some interesting libraries for any languages that you might be interested in. Focus on Go, but this is what you will touch on for .NET, for TypeScript. For Ruby, they have the Ruby VM that does AST analysis. In Python, all you do is import AST, and you can start doing like generating AST from code and do an analysis on that. And these are other resources. This one in particular, the Georgia Tech software analysis videos are found on YouTube. They have a whole library of lectures of software analysis that are very approachable, very easy to understand. I really like them. There's a class on compilers on Udacity that's very nice too. And there's Crafting Interpreters book. If you are into math, like me, then there's graph and set theory. It's one of the main areas to look into as well. And that's it. If you have any questions, let me know. Okay. Cool. Oh, yes. Sorry, I wasn't looking. With the SemGrep page, yeah, I'll play with it. And then I have found some nice results. I mean, the more that they have developed it, the less you need to use CodeQL or write some of these other custom tools, to be honest. It's pretty great. There are some times that I'm like try to get it to work on to solve a particular issue or program or find a particular bug. And some of the results are a little bit not exactly what I expect, or I wanted to, or maybe I expected more than what it currently does. But I think I think they continue to do a great job there. Yeah. Yeah. Yes. Yes, that's a big problem with CodeQL, and actually I meant to do that as a bullet point, how difficult it is to read their documentation, because the way that it's implemented for different languages is so different that the documentation for C++, for instance, is a great tool for C++. There's a lot of resources for figuring out how to write queries for C++, but for Go, then you start, finding issues in the documentation. The best way for that, the best documentation that I've seen for that is just, going crazy over their own docs. But then Trilobits does have this site called AppSec.guide, and then they have a whole resource on CodeQL too that you might like. Yeah. Cool. Cool. Thank you, folks.